In this video, we are going to continue our look at infinite series of real numbers. We will start with what I've called here the Cauchy Criterion for infinite series. And then the other two results that we will have in this video are consequences of this Cauchy Criterion. So one of them is the very famous, critically important Divergence Test. And then we will wrap up with a look at absolute convergence of series. Again, in these videos that I'm doing now for Real Analysis 1, looking at series of numbers, I expect that you have studied series already in something like a calculus course. If you have not, I actually have my calculus videos available, so you can actually see me teaching series of numbers kind of without necessarily all of the rigor in the background, but just kind of going through what it means to create an infinite series. Let's remind ourselves of when such a series converges. We say that an infinite series of numbers, here I'm just denoting it as sigma a sub k, where this could start at k equals 0, k equals 1, whatever, but it goes through the natural numbers off to infinity, so it's an infinite sum. It converges to a number L if the associated sequence of partial sums converges as a sequence to L. So that's our key perspective here, is that when we're talking about an infinite series, like we're trying to add up infinitely many terms, you cannot sit there and add up an infinite list of numbers. But when we pass to the associated sequence of partial sums, can we look at that sequence, apply our sequence tools, and conclude that that sequence converges? So sticking with this idea that from the sequence of partial sums, we get knowledge of the series, this is the Cauchy Criterion. We say that the series a sub k converges if and only if, for any choice of positive number epsilon, there's a threshold index capital N from the set of natural numbers, so that if you were to take any two indices beyond N and look at this sum here, so it's the absolute value of the terms starting with n plus 1 going up through m. If you do this sum, it is less than the epsilon that you identified at the beginning. Now, it's not too critically important that this start with little n plus 1. If you think about what it means to take any arbitrary pair of indices beyond the threshold index capital N, what we're really saying is just add up such a list of consecutive terms. Any such sum of consecutive terms beyond the threshold should be less than epsilon. Let's prove this. It's a very fast proof because, it's going to come down to studying the sequence of partial sums. I think I can actually fit it right here. We will do the if and only if double implication at the same time. I'm not going to write this out with words. I'm just going to be kind of casual with how I present this proof. So let's say AK converges if and only if the sequence S sub n converges. And then that happens if and only if S sub n is Cauchy. So we're working here with the real numbers. And then my next if and only if is really just a statement of the definition of a Cauchy sequence. So for all epsilon greater than 0, there exists a threshold index capital N such that for all pairings little m greater than or equal to little n greater than or equal to the threshold, S sub m minus S sub n is less than epsilon. And then all we need to do now is translate this difference in partial sums back to the series terms. So my next if and only if is going to be the same start, and then I'm just going to rewrite this in an equivalent way. For all epsilon greater than 0, there exists a threshold index, capital N, such that for all m greater than or equal to n greater than or equal to capital N, let me write out S sub n as an actual sum. I was going to do sigma notation, but I think I will just write a1 plus dot 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 plus an plus 1 plus dot 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 plus a sub m. Okay, this sum is this mth partial sum of the first mth terms. And I'm going to subtract from that a1 plus dot 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 plus an. That needs to be less than epsilon. I will actually wrap this up here. Now I'll take it one step further. This is going to cancel with that. And so this is like saying exactly the statement that we want. Most of these lines are really just rephrasing the exact same idea. So the if and only if forwards and backwards directions here should both seem very immediate. Starting here, a sub n plus 1. Okay. So this proof was not very hard because it's really like saying, well, the series converges if and only if the sequence of partial sums converges, which by the Cauchy criterion for sequences means that the sequence is Cauchy, and then we just kind of spell out what it means to say that the sequence of partial sums is Cauchy, and it just immediately leads to the conclusion that we're looking for. One little issue here that might have upset you when I wrote it down was I assumed that I was indexing here from 1, but notice that it actually doesn't matter. Whether I start with a sub 0 or a sub 1 or a sub 2, the beginning of the summation here cancels out. So perhaps I was almost too precise here when I wrote a sub 1, but those terms cancel out, and it's just this tail starting at little n plus 1 that remains when you do this subtraction here. All right, so that is the Cauchy criterion for series. In and of itself, I don't think it's too useful, but it has an extremely useful corollary. So let's take a look at the divergence test. So here's one of the most important facts about infinite series of real numbers. If the series converges, then it must be the case that the individual terms that we're adding to each other, those terms must shrink to 0. So let's immediately prove this, and then we'll talk about some consequences. Proof. Notice here the hypothesis is that the series converges, so we know that for free. Let epsilon be greater than 0. Since the series a sub k converges, we know that the sequence of partial sums is Cauchy. So we can choose some threshold index capital N so that for all m greater than or equal to n greater than or equal to that threshold, the difference between the little mth and little nth partial sums is less than epsilon. In particular, I want to take two partial sums which differ by only a term. If you think back to the results we had a moment ago where we were adding up a list of consecutive series terms between two particular series terms, we can actually shrink that list to just a single element. So what I'm going to do is choose k greater than the threshold so that k minus 1 is greater than or equal to the threshold. I just want to make sure I'm within the tail beyond the threshold. And notice that s sub k minus s sub k minus 1, well, both of these subscripts are greater than or equal to the threshold n, so we know that the result will be less than epsilon by this statement, but also we can say that literally the difference between these two consecutive partial sums is just the kth term. And that's really it, because now we're saying that for any epsilon greater than 0, you can identify an index capital N so that for all k beyond the index, the size of the kth term is less than epsilon. That tells you that these terms can be forced arbitrarily small beyond some threshold, and therefore the sequence of associated terms goes to 0. All right. So this is like a corollary of the previous result, where we set up our partial sums so that they differ by only a term. So instead of adding a bunch of things together, we're really just looking at one term at a time. Take the contrapositive of this statement. The contrapositive is arguably the more important statement. I'll call it a corollary. This is the contrapositive. If it's not the case that a sub k goes to 0, so all right, if a sub k does not converge to 0, then the series diverges. And that gives you a test for divergence. If you can look at a series, let me say about 2k plus 1 divided by 4k minus, I don't know, 5. And you want to start analyzing, does this series converge? You could actually recognize that if you look at this term and let k go to infinity, this goes to a half. So what I'm trying to add up, the terms get closer and closer to a half. That's not going to converge. So if your individual terms here do not go to zero, either they go to a non-zero number or they just don't converge to anything, then there's no point taking the series analysis any further. Your infinite series diverges. Okay, so this would be divergent. It's also important here to recognize that this is not an if and only if statement. We have a very famous divergent series whose terms do go to zero, and that's the harmonic series. So the terms 1 over k shrink to zero, but this diverges. Okay. So if your series converges, then it must be the case that the terms that you are adding together go to zero. Conversely, sorry, not conversely, contrapositively, taking the contrapositive, if the terms do not go to zero, then the series diverges. And again, that gives you a very quick test. This should probably always be the first thing you think of when you look at a series and you're actually trying to decide if it converges or not. Just take a moment just to ask yourself, does this actually go to zero? If it does, you are not done because it still might diverge, but it's worth investigating further. If it does not go to zero, you're done. The series diverges. I want to wrap up this video with a brief discussion of absolute convergence. If you have an infinite summation of real numbers where some of the numbers are positive and some of them are negative, perhaps that sum will actually converge because of some cancellation happening between the positive terms and the negative terms. So maybe you're adding some positive numbers, but the negative numbers are kind of wiping out the effect, and your sum actually converges to a real number. But what if you had such a series where you have alternating signs and you said, let's force all of the terms to be non-negative so that we won't have any more canceling action because if anything, the terms are just compiling a bunch of positive numbers. If you still get convergence, then we say the original series converges absolutely. It's like it converges so well that even forcing all of the terms to have the same sign doesn't break the convergence. That's absolute convergence. When you hear absolute convergence, think absolute value, because we also have other ways to characterize convergence. So absolute convergence, remember that's referring to absolute values. So if your original series, when you make all of the terms non-negative, still converges, it converges absolutely. It's possible, though, for a series to converge because of that canceling, some positive, some negative, it all wipes out. And when you make all of the terms non-negative, you break the convergence, the resulting series diverges. When that happens, we say the original series only converges conditionally. It really does need to have the balancing act between the positive and negative contributions. Let me give you just a really quick example of that. I'm not going to prove it in this video. We will talk about this a little bit later in a future video. But if you look at the infinite series that looks like -1 to the k divided by k, this is what you could call the alternating harmonic series. We start to expand it. When k equals 1, we get -1 plus a half minus a third plus a fourth minus a fifth, etc. Here's what I mean by that kind of canceling out. So, we add a whole half to it, but then we're subtracting, and we add back, but then we subtract. This converges. But when you take the absolute value of all of these terms to force them all to be non-negative, what you end up with is the divergent harmonic series. So this alternating harmonic series converges, but only conditionally. It does not converge absolutely. It only converges conditionally. Okay, I'm not going to prove this result in this video. We will talk about what are called alternating series a little bit later. The absolute convergence test says that if the series of terms, which are all non-negative, converges, then that is enough to know that the original series converges. That shouldn't surprise you, because here we're saying if everything is, let's say, positive, Then if you allow some of the terms to flip to negative, if anything, you might like converge a little bit more easily. So again, that shouldn't surprise you, but we will prove this. I'm going to step aside, erase this, come back and do the proof, but I want you to try to prove this on your own first. I'm telling you that it is a corollary of that Cauchy criterion for series that we opened with. So see if you can apply that opening statement, that Cauchy criterion for series, to these two series. Here's how I will write down this proof. Let epsilon greater than 0 be given. We already know that this series converges, so we can immediately apply the Cauchy criterion to it. Choose, actually, let me make that clear since we have two series here. Don't want the reader to be confused. Given that this series converges by the Cauchy criterion, we can choose a threshold index capital N so that for all little m greater than or equal to n greater than or equal to capital N, we have that I'm going to start with a giant absolute value that you really don't need. So the absolute value of the terms in this series, starting with little n plus 1 and going up through m. So that was the Cauchy criterion as we stated it in the beginning. In other words, it's the difference between two partial sums. So we have absolute value of a sub n plus 1 plus all the way through the absolute value of a sub m is less than epsilon. This is directly applying that opening statement to this series, given that it converges. You can leave this as it is. I'm going to run out of room if I rewrite it, so I'm just going to erase the absolute values here because the left-hand side is non-negative, so there's no need for these enclosing absolute values. I just wrote them in the first place in order to make it really match the opening statement. Notice, for any such pair of indices, it follows by the triangle inequality that if I look at the same kind of sum construction, but for this series, we do need those absolute values because we don't know if these terms are positive or negative. So we would have the sum starting with n plus 1 and going up through am. This is the quantity that we want to understand in order to apply the Cauchy criterion to this mysterious series. But with the triangle inequality, we can say that the absolute value of the sum is less than or equal to the sum of the absolute values. And that is exactly the expression that we have here. So we know already that it's less than epsilon. And thus, this series converges by the Cauchy criterion. Oops, that was supposed to be a and symbol. All right. I think here where we have the triangle inequality, you can really see what I mean by it's easier for this series to converge than this one. Because, here it's like we could have some canceling out between positive and negative terms. Here, everything is non-negative. Okay, so if this series converges, then it must follow that this one also converges. All right, that wraps up this video. We are going to continue our look at series in the next video.